G'day. In this video we will look at how to solve linear simultaneous equations involving 2 and 3 variables. First of all though, what is a linear equation? Well, a linear equation has two variables where each variable is raised to the power of 1. But what is a variable? A variable, of course, is any symbol, usually a letter of the alphabet, that represents some sort of quantity that can change according to given information. And here's an example. 4x equals 6 is a linear equation because it has an equals in it, or 4y equals 6 is another linear equation. Each of the variables, x and y, are raised to the power of 1. In other words, x to the power of 1 is x, y to the power of 1 is y. And they're examples of one variable, one letter. And if we solve those two equations for x and y, we obtain a horizontal line for 4y equals 6 and a vertical line for 4x equals 6. Here's an example of two variables, 2x plus 5y equals 1, where the two variables are x and y. And what do you think the graph of that would look like? It's a linear equation. Linear, of course, means straight line, doesn't it? So in this case, it will be a slant or a sloping straight line. What about 3 dimensions? 3 variables. Something like that one. We have variables x, y, and z. And in this particular case, if we sketch it, we obtain a 3-dimensional plane. What we are going to do is look at ways of solving equations involving 2 or 3 variables, and that will occur in the second video. But in this first one, we will look at the conditions that allow us to obtain a solution. The set of equations that we will be solving are called simultaneous equations. Here are some examples using 2 variables and 3 variables. Firstly, 2 variables. We have our 2 equations, x plus y equals 7 and 3x minus y equals 1. That's a pair of simultaneous equations. And for 3 variables, we have 3 equations with the 3 variables x, y, and z. Each of those can be solved, possibly, according to the conditions we will set out. Now let's look at 2 variables firstly. When we say that we are going to solve the simultaneous equations in 2 variables, what do you think it means? It means 2 things. Firstly, to find the value of the variables that make both equations true at the same time. And also, in terms of a graph, it represents the point on the graph where the 2 lines intersect. Something like that. We have our 2 equations, x plus y equals 7, 3x minus y equals 1. And if we draw the graph of the 2 linear equations, you can see that there is a point of intersection at x equals 2 and y equals 5. So solving this pair of simultaneous equations means finding that point of intersection. And you'll find that if you substitute x equals 2 and y equals 5 in each of the equations, it makes each equation true. For example, the first equation says x plus y equals 7. That means 2 plus 5 equals 7. And the second equation, 3x minus y equals 1, means 3 times 2 minus 5 equals 1, which is true, of course. However, it can happen that the 2 lines do not intersect, and this will occur when the 2 lines are parallel, like that. Now the question remains, without actually drawing the graphs of the simultaneous equations in 2 variables, how can we determine that the lines will be parallel or they will intersect? And this is the key to it in terms of matrices. We find the determinant. Now let's look at the general case for a pair of simultaneous equations involving 2 variables, x and y. We can write each equation as you can see there. A subscript 1x plus b1y equals c1 and a2x plus b2y equals c2, where a1, b1 and c1 and a2, b2 and c2 are given constants. And in terms of matrices, if we look at the coefficients of the variables, which are A1, B1, A2 and B2, we call that the coefficient matrix, and if we represent it by the letter capital A, we can write it as a matrix, like that. Now, to evaluate the determinant of that matrix A, think of it as a cross multiply. You can write the determinant in 3 different ways. we can either write it as det, determinant A, or put brackets around the A, or the vertical lines around the letter A. Either of the three forms is commonly used. Now the determinant of A is the product of A1, B2, and then minus the product of B1 and A2. In other words, A1, B2 minus B1, A2. Something like the cross multiplying. Why that's the case we will look at it a little later on. And this is the important conclusion we can make from the value of the determinant. If it equals 0, it means the lines on the graph will be parallel, and if the determinant is not 0, there is a point of intersection. In other words, the two equations have a point of solution. Now let's look at an example of that. Here are our two equations, simultaneous equations. If we write the coefficient matrix, we have A equals, as you can see there, and then working out the determinant, it'll be 4 times 9 minus 6 times 6, which is 0. So we've concluded that the determinant is 0. So that tells us that the two lines will be parallel, and indeed they are. If you actually drew the graph, that's what it will look like. Now let's look at another example of that. Two different equations. The coefficient matrix is given there, and working out the determinant comes out to be -5. It's not 0, so that means there is a point of intersection. In fact, if you drew the graph for these two equations, you can see there is a point of intersection. In this case at x equals 4 and y equals 1. Now let's look at why exactly the value of the determinant tells us there is a point of intersection. Here are our general equations that we had previously. Let's say we want to go about solving those equations algebraically. That means we want the solutions for x and y. One way would be to combine the two equations into one equation by eliminating the variable y, and this is how we can do that. Let's label our two equations 1 and 2. Firstly, multiply equation 1 by the coefficient b2, as you can see there, and we can call the resultant equation 3. And now multiply equation 2 by b1, and we obtain another equation b4. Now do you notice the coefficient in each equation 3 and 4 of the variable y is b1, b2? So we can eliminate those two values by subtracting one equation from the other. Let's say equation 3 minus equation 4, like that. So when you minus equation 4 from equation 3, you obtain what's shown there. So we have eliminated variable y, and now let's simplify what we have left. We can take out a factor of x, like that, and then transposing that to get x on its own, we can divide both sides by what's in the bracket, a1 b2 minus a2 b1, and there we are. We have our value for x in terms of the constants a1 b1, a2 b2 and c1 c2. Now using a similar approach, but this time eliminating the variable x from each equation, we can obtain the expression for y in terms of the same constants. And there it is. Do you notice something about the denominator in each one? That's right, a1 b2 minus a2 b1 is our determinant, isn't it? And we're dividing that into 1 in each case. Now remember that 1 divided by any value is only possible when the denominator is not 0. So in this case, in each equation, a1 b2 minus a2 b1 can't be 0. And because the denominator is our determinant, we can say that our determinant can't be 0 if there's going to be a solution for x and y. Okay, that covers 2 variables. The case for 3 variables is a bit more challenging, so let's look at it. Here's a general set of 3 equations involving our 3 variables x, y and z. To obtain the determinant, you have a choice, as you'll see in a little while, but let's say we are going to use row 1 of our coefficient matrix. There's our coefficient matrix, and row 1 consists of a1, b1 and c1. And this is the process we follow if we are going to use row 1. The determinant will be, now what you do, starting with the first value in A1, in row A1, is cross off the column containing A1 and the row containing A1. As you can see there with those two lines, the constants that remain, which are the ones in that yellow box, are the values that you put in the determinant, like that. And because we're using coefficient A1, that goes in front, and there's a plus, and you'll see why in a moment. Now moving to the next value in row 1, which is B1, we do the same sort of thing. There we go. We cross off the row and column containing B1, and the 4 values remaining become our second determinant, like that, and B1 goes in front, and there's a minus. Have you noticed what's happening? The sign alternates, so we had plus A1 and then minus B1. So what do you think the next one will be? There we go. The third value in row 1, which is C1, cross off the row and column for that, and what we have remaining is what you can see there. And then evaluating each of those determinants, there's our expression for the determinant of that system of equations involving 3 variables. Not something you should memorize, but you should remember the method. And that expression is obtained by using row 1. However, as I mentioned, we can use any row or column in exactly the same way to work out the value of the determinant. And I'll just give you an example of that. There's our coefficient matrix. And what we do is assign alternating pluses and minuses to each constant, as you can see there in brackets. Now let's suppose this time, instead of using row 1, we use column 2 to work out the determinant. And that's what you obtain, starting with the term B1 in column 2 and then B2 and so on. Notice again the alternating minus plus minus. And if we use, let's say, row 3, we obtain a different expression. So different expressions, but when you substitute the actual values for the constants, you'll see that each one provides the same value for the determinant. And just to convince you of that, let's suppose our coefficient matrix is what's shown there. If we use column 2, the value for the determinant comes out to be 0. If we use row 3, it also comes out to be 0. And of course, what does it mean when we have 0 for the determinant? It means that there is no solution. So if we actually tried algebraically to work out the values of A1, B1, C1 and so on, we would find that it's not possible because the determinant is 0. What do you think it means in terms of a graph? When we are referring to 3 variables, x, y and z. Each equation represents a plane. So it would mean that 2 of those planes, at least, are parallel. There is no common point of solution. In the next video, we will look at the method using matrix operations to find solutions to simultaneous equations involving 2 and 3 variables. So until the next video, bye-bye.